Hello, hello, hello. This video is meant for people who have already watched my famous lecture number 16 of 802. And they should remember that what I demonstrate there, I derive it first using Maxwell's equations, and then I demonstrate that the potential difference between 2 points in a circuit is no longer defined when we have an induced EMF. 2 voltmeters connected to exactly the same 2 points can measure different values. Even the polarity can be different. And that's what I demonstrated at the end of my lecture 16. However, there are people who probably don't have a very solid physics background who emotionally cannot handle that. They have a religious belief that the potential difference, which we define as the integral of E dot dl, between 2 points, always has to be the same. Cannot be different for different paths. It cannot be different for 2 different voltmeters. If they are attached to the same points, they claim they must measure the same potential difference. It's true that that would be the case if Kirchhoff's loop rule would always work. But Kirchhoff's loop rule doesn't always work. Maxwell's equations always work. Faraday's law is one of the 4 Maxwell's equations. Kirchhoff's loop rule is a special case of Faraday's law. So therefore, Kirchhoff's loop rule is not one of Maxwell's equations. So, what are the arguments of the people who have a religious problem with the outcome of the demo? One classic argument is they claim that Kirchhoff's loop rule always works. Apart from the fact that this is not true, the sad part is that almost all college physics books, Halliday and Resnick, Giancoli, Ohanian, Young and Freeman, they all, when they deal with self-inductors, with solenoids, and they derive the equations, they all say, let us now use Kirchhoff's loop rule. That statement is a crime, because they don't use Kirchhoff's loop rule, but they pretend they do. I discussed that issue in a previous video, which I call 5 plus 3 minus 8 is 0. So these books certainly have the equations right, because they write down 5 plus 3 minus 8 is 0, but that is not Kirchhoff's loop rule. So they get the right answer, but they use the wrong language. I will not address that issue any longer. I've hit that hard enough. So why am I doing this video? The other 2 arguments that are being used by people whose knowledge of physics is perhaps a little limited. The other 2 arguments are the following. In the derivation that Walter Lewin does in class, he forgets to take one closed loop into account. Well, of course they're wrong. Yeah, no, they're right, I didn't take that into account. And the reason why I didn't take it into account is I will demonstrate today that that extra loop doesn't add anything new. it's a redundant loop. So even though they're right, they overlook the fact that if you take that extra loop into account, that you learn nothing more. Then there is another argument that is being used, why my derivations are wrong and therefore why the demonstration is a cheat. They really believe that I overlooked to take the inductance of my wires into account. Well, I didn't take the inductance into account, as I will show you today, because you don't have to take them into account. So if you're ready for this, let's go over my derivations and look again at the diagram that I have in my lectures. This is a voltmeter V1 and this is a voltmeter V2. Both measure the potential difference, if you call that potential difference, between point A and point D. These wires have near zero resistance. This wire has near zero resistance. So both are attached to point A and point D. Here is a resistor R1, here is a resistor R2. And right inside this area we put an electromagnet. It's a long one, at least 30 centimeters long. It sticks out of the board at least this much and goes into the board. And when we turn that electromagnet on, there is a changing magnetic field in this area. And that causes an induced EMF in this loop. It also induces an induced EMF, of course, in this loop. And that's the one that these people think I overlooked. They think I overlooked this loop. So let us now see how we solve this problem. We choose a moment that the induced EMF, due to Faraday's law, in this loop, and therefore also in this loop, is 1 volt. So I pick the moment that my magnetic flux changes in here, because I turn on the electromagnet, is such that I get an EMF, electromotive force of 1 volt. I call that EMF this curved letter E. R1 is 100 ohms, R2 is 900 ohms, so the current that is going to run here is 1 milliampere. The resistance of these voltmeters is more than 100 million ohms. Keep that in mind, that's going to be very important. I call this loop 1, this loop 2, and this loop 3, and this loop I call loop number 4. That's the one that I didn't take into account, remember? How do you solve a problem like this? Well, what I always teach my students in 802, when you have more than one closed loops, the safest way to solve this is you assume that the current is going around here. I call that I1. You assume that the current is going around here. I call that I. And you assume that the current is going around here, which is I2. If you do that, you can never go wrong anymore. Surely, when you deal with the potential difference over this resistance, you have to take I1 into account, and I, of course, that goes without saying. But it's a very safe way to solve this problem. So let us now first go to loop 1. I want you to know that through this loop there is really no magnetic flux change. It is negligibly small. Of course at MIT we have measured that. This magnetic field, this changing magnetic field, is very strong here. But because of the geometry of our electromagnet, the E field, the magnetic field, both in this loop and in this loop, are not even measurable anymore. So that means in this loop, Kirchhoff loop rule holds, closed loop integral of E dot dl must be 0. It's also 0 in this loop, it is not 0 in this loop, and it is not 0 in this loop. So if you're ready, let's start with loop 1. I1 is going up in this direction. This point has a higher potential than that point because of this current. This is called my positive current, and so the integral E dot dl from here to here is I1 times R of I. I1 times R of I. The positive current is going down through here, so the potential difference between here and here is I1 times R1 plus I1 times R1. But now there is here a current going up here, and this current going up makes this point a higher potential than this, and therefore we have to subtract IR1 minus IR1, and that is 0, because Kirchhoff loop rule demands that the closed loop integral is 0. Keep in mind that these wires have near 0 resistance, so there is no potential difference across those wires. Now, did Walter Lewin make the blunder to not take into account the inductance of the wires? When I do the experiment, you will see that the current of 1 milliampere rises very quickly to that maximum value in about 1 millisecond. So the current change, amperes per second, is very roughly a maximum of a milliampere divided by a millisecond, and that is 1 ampere per second. So if this closed loop integral were not 0, because I take into account the inductance of the wires, I should have put here a term minus L di dt. The di dt then is 1 ampere per second. The self-inductance of a 1 meter copper wire of 3 millimeters thick is 1 millionth of a Henry. So 1 millionth times 1 will give you a voltage of 1 millionth of a volt. And that is why obviously no sane person will take the inductance of the wires into account. We're dealing here with voltages like 1 volt. And then to take a 1 millionth of a volt into account is ludicrous. So did I ignore the inductances of the wires? Yes. Should I have ignored it? Yes, of course. Now let's go to the second loop. So again, these wires have no resistance. Inductance can be ignored. So the current I goes up here. So that is I times R1. I times R1. It goes down here. This is also the plus direction. So I have to add I times R2. Plus I times R2. But now there is a current here in this direction. Therefore I have to subtract I1 times R1 minus I1 times R1. There's also a current here which is I2, and so I also have to subtract I2 times R2, because this is my positive direction of current, so this is my negative direction. So minus I2 R2. That is now E. That is the EMF. That is not zero, because in this closed loop, Kirchhoff's loop rule doesn't hold. Faraday's law holds. And that's the 1 volt EMF at a particular moment in time, which is related to my demo. Let's now go to this loop. Again, in this loop, the observed magnetic field change is so small we could not even measure it. So you can apply Kirchhoff's loop rule in this loop. I propose you now try to do that on your own. You get an I2 R2, you get an I2 RI, I2 R2, I2 RI, but now you have to subtract I times R2 because this current is in this direction. So it is minus I times R2, and that now is zero. Kirchhoff's loop rule holds in that circuit. Now comes loop number 4, which Walter Lewin forgot. How could he possibly be so ignorant? Professor of physics at MIT, famous institution. How on earth could he possibly overlook the closed loop integral of loop number 4? Let's take a look at it. The closed loop integral of this loop is obviously EMF, because this magnetic flux change for sure happens in this closed loop. So I1 is going up here, that's my positive direction, so that is I1 times R of I, I1 times R of I. I2 is going down here, so that's my positive direction, so that's I2 times R of I. Plus I2 times R of I. And that is that same E as we have here. So now I've been a good boy. I took this loop into account. Look at I1 R1. I1 R1. This current is immensely small because this resistor is 100 mega ohms. This is so small compared to the current that will go through here that R1 I1 is negligibly small. It's probably 1,000,000 times smaller than IR1. So you can comfortably neglect the term I1 R1. For the same reason is I2 R2 also probably 1,000,000 times smaller than IR2. So here you can also forget I2 R2, I1 R1 can go and I2 R2 can go. So let's now go back to this equation. And this can be ignored. If you don't ignore it, then well, you just add something like a fraction of a millionth of a volt. Fine. So look at this equation now. So you have that I1 Ri equals IR1. What is this I1 R of I? That is the current going through here. It's the potential difference I1 Ri, I1 R of I, is the potential difference over this voltmeter. That is the one we want to know. That is the V1 that we are going to calculate. Just like here, I2 times Ri here is the potential difference over this voltmeter. So from here we get that I1 R of I, that's the one that we want to know is I R1. And now we go to this equation, I2 Ri is IR2. This is the potential difference measured by voltmeter 1, and this is measured by voltmeter number 2. Look at this equation and look at this equation. So IR1 is the same as I1 R of I, and IR2 is the same as I2 R of I. Therefore, this equation is identical to that equation. Loop number 4 is redundant. I can leave loop number 4 out. I gain nothing when I add it. So that is why Walter Lewin did not take loop number 4 into account. Because he did his homework. And the people who say he didn't take loop 4 into account, they are right, but they didn't do their homework. They didn't calculate, they didn't show, probably because they don't know enough physics, that you don't need loop number 4. You can add it, that's fine. But you learn nothing new. So now, let's look at these numbers. IR1. I is 1,000th of an amperes, and R1 is 100 ohms. So this I1 R of I is 0.1 volts. Because IR1 is I1 Ri. And this voltmeter registered I2 R of I, which is IR2. I is 10 to the minus amperes, R2 is 900 ohms, so IR2 is 0.9 volts. So the voltmeter on the right will register 0.9 volts, and the voltmeter to the left will measure 0.1 volt. That's non-negotiable. It's the result of Faraday's law. However, be careful. This 0.1 volt is the result of a current flowing in this direction. This 0.9 volt is the result of a current flowing in this direction. Both voltmeters obviously were attached in such a way that the plus side of the voltmeters are both in this direction. That's essential. They have to be exactly attached to point A and D in the same way. So if the current is running in this direction, then the potential here is higher than there. So it's true that the magnitude of V1 is 0.1 volts, but the polarity is negative. So this voltmeter will show minus 0.1 volt, and this voltmeter will show plus 0.9 volts. End of story. Did I do this video to convince the herds of semi-uneducated physicists, to convince them that no, I didn't make any mistakes, and yes, the demo at the end is 100% kosher? No, I didn't do that to convince them, because their belief is a religious belief that will never change. So why did I do this video? I did it only because many viewers ask me, what is wrong with the arguments of these people who say Walter Lewin did everything wrong? I never argued with those people directly, for a simple reason: I teach physics, and I don't argue with people who think they know, but who don't. So I never argued with these people, but I feel an obligation then, perhaps, to many viewers who say, please let us know what is wrong in their arguments. And that's what I have done today. So, there are people who think that Kirchhoff loop rule always applies. Wrong. There are people who say you overlooked one loop 4. They are right, I overlooked that loop because it can be overlooked. They say you didn't take into account the inductance of the wires. They are right, I didn't, because it would be absurd, it would be ludicrous to take them into account. None of the people who think that my lecture 16 is a fraud will ever be convinced. I know that from an experience of 50 years. They will dig their heels in no matter what. I respect their opinions, I really do. They really believe that what I did is wrong. I think they are entitled to believe what they want to believe. I believe in the freedom of religion. The freedom of religion is a cornerstone of all civilized democracies. However, don't confuse religion with science, because their religion cannot change Maxwell's equations. Alright, we are still friends, I hope, and I also feel like the people who just lack the background of physics and therefore have this religious belief, they are also my friends. I really think so. As I said earlier, I respect their opinion, even though their opinion and their oppositions are just dead wrong. Okay? Have a nice day and take care.